Now that we've talked about these angular quantities and rotations as well as maintaining circular motion, we're now going to have a brief discussion about how it actually starts up. So if you take an object like this box on the screen and you push on it, uh, what you'll notice is different things happen depending on where you push. So if you grab any physical object and you push right about near that object's center, so we apply a force like this, what you'll find is you'll get a nice normal looking acceleration. And that's a pretty standard thing that happens. However, we can get a difference in things that happen if we push at different locations. So if instead we push up near the edge of our object, what you'll actually notice is you will get more of a rotation or an angular acceleration. Right? And this here is one of the main ways in which motion can differ for an actual object depending on where you push. Now, when it comes to generating this second style rotation, we have to look at not only the force, but where it is applied. And this is what's going to differentiate what we're going to do now from what we did before with forces. Now, just like with forces though, we have physics tools that deal with this. So when we're pushing far away from the center or center of mass of an object, creating a rotation, we actually figure out how that rotation is going to behave using a tool known as a torque. And this is the exact same torque that you would find in items such as a torque wrench. A torque wrench is a wrench specifically designed to create a torque. Now, for this torque, it is another mathematically defined quantity. And what you'll notice is this torque, which is the tau or the T looking symbol in the red box here, involves two quantities. First of all, it involves a vector r, and secondly, it involves a force. In between them is a vector product. Now, in terms of dealing with them, what is r? Well, plainly put, r is a vector from the axis of rotation, or wherever things going to spin around, which is usually the middle of our object, to where the force is applied. Right, so this here is r. And so what you'll notice is if we're applying something far away from the center of mass, we'll get more rotation than we would if we push directly on the center of mass. Now, this vector product here actually takes into account three different things. So even though we have r crossed with f here, there are three independent quantities that are going to affect this. How big r is, how big f is, and because we're dealing with a vector product, the angle between them also matters. This torque quantity is maximized at a 90-degree angle and actually minimized when two things are parallel. So what that means is if we were to apply a different force, such as say right here, right in the middle, we could have this blue force. This would give us an r that's roughly speaking parallel to the force we just applied. And this would actually give us a very small torque because the angle between them does matter. Now, when it comes to dealing with two-dimensional rotation problems, although you can use this cross product directly, it's not the fastest way of doing things. Interestingly enough, for two-dimensional problems, where you can draw them all on a flat piece of paper, we're actually usually better off calculating the magnitude of the torque and the direction of the torque separately. So this is a bit of a shortcut, but what you can do is instead of doing r crossed with f, you can find the magnitude of the torque by taking the magnitude of r, the magnitude of f, and multiplying them by the sine of the angle between them. And for the direction, you can use the same sign convention we used before, in which positive things are counterclockwise and negative things are clockwise. So in this instance here, where we have this black colored force up at the top, what you'll notice is pushing on the top is going to try to make this thing rotate clockwise. So you would say that this torque here is negative. And that's sometimes an easier way to deal with this than doing the cross product every single time. Now, this type of thing behaves very similar to a force. If we have multiple torques, we can add them all together to find a net or total torque, just like we could do with forces. And this total or net torque is related directly to the angular acceleration, much like how the net force was related to the regular acceleration. The only difference here is in place of the mass, we use a new quantity I, known as the moment of inertia. It behaves very, very similar to a mass, and we'll be talking about how to calculate it a little later on. But the idea is, problem solving wise, this becomes very, very similar to what we did when dealing with forces. We just have a new quantity here known as a torque. It's calculated a bit differently, but it behaves the same general rules that are outlined in green there. Now, the final thing that we'll discuss here is actually the hardest part of this, and that is determining the angle theta here. So if we have a force in green and a radial vector in r, the question is, well, how do we determine the angle between them? This is one of the few cases in which the angle between them is actually defined uh, by the angle tail to tail. So if we take these two things and we line them up, the angle that we're actually looking for is this angle here. Now, there are a couple of different ways of dealing with this. You can move them around, line them up tail to tail, and draw the angle between them. Or alternatively, what you can do is you can actually take your force vector, extend it outwards in a straight line, and then use that to find the angle theta. So keep in mind, it is this angle that you need, right? You need theta here. This may not be always the angle that you've been provided with in the question. So you can draw it like this, or you can draw it like this. They are the same, as you'll notice. But make sure that you are defining your angles properly, because it's required to use this simplified methodology. The cross product always works, right? But this may be faster in a large variety of situations.